Hi again to everyone on Zoom. So we're talking about moving away from spherical particles or circular particles. And I'm going to work mostly in 2D here, but almost everything I say also works in 3D with, more exceptions and more other things, but it's just harder to draw everything and takes longer to talk about. So just a couple of ways that we might move away from circles. One option is to just elongate. So we can do an affine transformation like an ellipse. So that's an option. Another way is to start building particles out of disks. So we can build lots of different shapes, and there's kind of a continuous way to go. I can get out here and I can get back to a disk, kind of, but bumpy. I might also do an affine transformation on that and go back up here to the ellipse. The difference is, as I go from here to here, I need an infinite number of disks to actually move from here to here, and that'll turn out to be important. Another way I can go is to think about the other definition of a sphere, which is that it's the set of points that are all equidistant from a point. And so I could also think about all the points that are equidistant from a line. We call that a circular line, or you might call it a spherocylinder in 3D. That's all the points that are equidistant from this line, but you could extend that to polygons. So all the points are equidistant from a triangle, from a pentagon, I guess would be 5. That's one other option of a way to go. Another sort of way to go is to think about shapes that all have the property that if you put parallel lines across them, they're the same distance. So the circle has this property. Every parallel line set is the same distance apart, but that's not the only shape that has that property. So these Rouleau triangles or generalizations of them are another possible way to go. And then finally, I'm going to talk about breaking shape down even further and allowing the shape to be one of the degrees of freedom in the problem, where it can actually change itself on its own. Okay, so just to sort of recap what we think happens at jamming, and this is only right at jamming. Okay, so there's a condition right at jamming, basically due to Maxwell. Well, he wasn't thinking about jamming, he was thinking about bars and struts and the stability of those things, but it works out to be the same thing. We can just sort of count up all the degrees of freedom in the problem, and we say there has to be a constraint for every degree of freedom in the problem. So on this side, I have degrees of freedom in the problem, and this is the side I have constraints on. The side of constraints is typically determined by the number of contacts, but there might be more than one constraint per contact. And so we have this C value, and in general, each contact might have a different number of constraints. So that's another possibility. You have to add sums in here to make that work. But that's all the constraints on this side. On this side, we have the total degrees of freedom. That depends on the number of particles that you have. So I have a certain number of particles, and I have a certain number of degrees of freedom per particle. Of course, again, the F could be dependent on which particle you are. So this could be sums over I's. Now I'm going to have to subtract off a bit, because in packings and things like that, I typically don't care if I move the whole packing around. So I have to subtract off the dimension to not care about that. If I'm in a situation where I could also rotate everything that I didn't care, I have to subtract off more D's. There'd be another set of things, but we'll be in situations where we only have to subtract off the dimension. But then we have to add one more thing on, because we're also going to compress them. And so there's a degree of freedom of changing the diameters of the particles or the sizes of the particles. So we have to add that on. So when we put all these things together, we can kind of consolidate it all and think about what's going to happen for a few cases. Okay, so let's start on the frictionless side. If there's no friction, then the value of C, which is the number of constraints per contact, we would typically think is just 1. So 1 constraint per contact. If we have a circle, there's 2 degrees of freedom in a circle. I don't care about the rotations of a circle, so I just have 2 here. And that tells me that the average number of contacts, which is 2 times the total number of contacts divided by n, that's the average number of contacts per particle, that'll be 4 minus 2 over n. And I put these minus 2 over n things, they come from this equation. Of course, if n is big, we don't care about them in some way, but if we were to really count and find out when it's really isostatic, we have to care about these little bits, because they make a big difference when n is 10 or 50, something like that. I can still tell the difference, so we have to care about those. But generally, you can think that circles should have 4 contacts per particle. Now, if I go to a non-circular particle, then all I do is change F. I've just changed the number of degrees of freedom per particle, and so now I get 6 here. So basically, I go from 4 to 6 when I add in rotations to the particle. Now, if I go to the frictional side of things, this number of constraints per contact becomes a little more interesting, because I have 2 possible constraints per contact. I have a tangential force and a normal force, but there's a relationship between them. And sometimes it's at the end of that relationship, and so they only represent one thing. Sometimes it's the middle, and sometimes there might not be any tangential force. So C really takes on a variable value between 1 and 2 for these kind of cases. For the circle, that's really all there is. There's just the 1 plus C. That's all the degrees of freedom per particle. And of course, that C might be different values, so it'll depend on that. But what we work out is then that there should be, it should be between 4 and 3 contacts per particle plus these little 1 over n contributions. So basically, for circular particles, if you have very low friction, you should expect 4. If you have very high friction, you should expect only 3 contacts per particle. And the same thing we can do for non-circular particles, where we just turn F into 3, and now we can go from 6 all the way down to 3. So you can have a total of 6 contacts if you wanted. Now this is a little bit, I don't know, it's a little bit disappointing that we can't find the number of contacts for the frictional case. But we can actually do something about that. So what we can imagine is that if we're in a frictional system, if we were isostatic, we'd already be stable. That is to say, there's only one point in the configuration space where I could be stable. You remember back to the very first talk that Ken gave, he wrote down this compatibility matrix C, and that compatibility matrix, if it's square, I can just solve it right away, and there's only one thing. So in that configuration space, there's only one point. And so I have that solution. So then I do know whether it's going to be isostatic. It will be regular old isostatic. It'll be on the 4 side. Now imagine I have one less contact. If I have one less contact, now the null space of this matrix has 1 degree of freedom. So there's a family, a one-dimensional family of solutions, and only the solutions that obey Coulomb's law can live on this thing. So there'll be some distribution of states that live on that one-dimensional thing. And of course, if I lost 2 contacts, now I would have a 2D space where I could live. And so all of these things would represent solutions to the possible solutions of the problem. It will be modulated again by the requirement that we have all normal forces are greater than 0. We're only pushing on these things, and that the friction was less than or equal to the ratio of the tangential to the normal force. That's Coulomb's law. I can't put more tangential force on than mu times the normal force. That's as much as I can do. And so that'll create a kind of overlay onto this dimensional space. Now this ends eventually. Eventually, if I take away enough contacts, I get to that 3 contacts per particle, and I no longer have any way to solve the problem if I go beyond that. But at that point, there's only one set of forces. So when we're on this side, there's a tremendous number of force sets that will solve the problem. But when we go further up and we have a big high dimensional space where all the solutions can live, there's only one force set. And so what you can sort of guess is that you can make a configurational entropy out of this idea. And basically it's the product of this real space and this force space. And so it's very small at one end because there's only one possibility, and it's very small at the other end. In the middle, it's big. And so you get this. And we can actually do this and work this out. So here, what I'm plotting is the probability that I will be isostatic in a frictional system when my frictional value is given here. So if I have very low friction, the chance that I'm isostatic is very high. It's basically 1. As I approach this, it's 1. Now, as I make friction steeper and steeper and steeper, the chance that I'm in isostaticity is going to get less and less and less. And the chance that I'll have one missing contact will grow up. And this happens over and over and over again. 1 contact relates to 2, to 3, to 4, to 5, to 6, 7. I lose more and more contacts as I go along. By the time I get back here, now, when I have really high friction, this is friction 1. So this is when the normal force is equal to the tangential force. This is friction 10. When the tangential force is 10 times the normal force, I like poke a stick in the ground and I really can't move this thing. On that end, now the chance of having 3 is 100%. And so that's what's on that side. Now, these dashed lines are the theory that I just outlined. And the dotted lines are simulations of this.
So can you just get to first of all, there is another line that starts from 1. What is this? Can you?
This line and this line?
Yeah, there's 100% probability of being isostatic. What is this line?
This line represents the probability that you're isostatic given that you have this friction. So my friction is 10 to the minus 2.
There's many lines. What's that particular line?
This line is isostatic. Yeah. This line is 1 missing contact, 2 missing contacts, 3 missing contacts.
But then the protocol matters for this isostaticity because I can actually tap and I can do something to actually get more coordination, right?
You could tap and do that. You would,
And so I will basically go away from this probability because I won't be isostatic anymore.
right, you would have to evolve this. So we have an evolution equation for this. If you were to evolve it by tapping,
Okay.
you can actually evolve this. And what will happen is, as you tap, you start out over here somewhere and you will start moving back along this curve as you
okay.
tap.
So
So it's like tapping is like removing friction. It's like slowly removing friction. Yeah, and we have an equation for that. And what more details you can look in the paper. But this bears out that this theory matches very, very well with what we actually measure when we do this. And you can do things like calculate the probability that you'll have 4 or 3 contacts is a function of mu, and that these solid lines are calculations directly from the theory, no adjustable parameters, and the dashed line and the points are from simulating this. So that's friction. So we kind of have a very good understanding what happens between isostaticity and friction. We go from 4 contacts to 3, or 6 contacts to 3 if we had rotations, if we added rotations to this problem. Okay, so that brings us back now. We've sort of solved the frictional side of things. When it's going to be isostatic, it's kind of always isostatic for the mu that it's at. That's the way you can kind of think about it. And so mu determines where you are between 4 and 3 and between 6 and 3. And it's determined statistically. That's the only way to determine it. But now we get back to the frictionless case, and it tells us something interesting. It says that as soon as I make my circle even slightly asymmetric, I should jump from 4 contacts per particle to 6 contacts per particle. So I have a circular packing, and I just stretch it a tiny amount, and now I need 6 contacts. It'll fall apart otherwise. So is that really true? So that's what this theory sort of says. Let's see what reality says. So now we're going to focus in on something like ellipses. Okay, so we're going to look at ellipses, and we're going to ask, do they jump instantaneously from 4 to 6 when we make them move? And in fact, it turns out they don't. So here I'm plotting what we would call acircularity. So it's how non-circular it is. And I don't know, it's really annoying that that's the way we did this. We should just turn these things around, but that's the way people did it. So, you know, I have to live with it. So because we wanted 4 on this side and 6 on this side, I don't know why. But I guess because its friction goes up here. But at any rate, so what you see is that if this parameter, which is what we're doing, is kind of a measure of how elongated it is. So it's what we really use is the square of the perimeter divided by 4 pi times the area. So that thing will be 1 if it's a circle. But the 4 pi is there to make it 1 if it's a circle, because you'll have 2 pi r squared, and you'll have pi r squared down here, and that'll give us 1 for the circle. For an ellipse, that's approximately just also the aspect ratio A over B. So that's roughly what you're thinking of here. So when the aspect ratio is close to a circle, we have 4 contacts per particle. And as we get less and less circular, our acircularity gets larger, get more and more elliptical, we jump up towards 6. Yes.
Some people just call that the isoparametric ratio.
Yes, other people call it the isoparametric ratio.
Normalized to be 1.
Totally agree. There's and a lot of people actually use the inverse of this. Exactly. So there's a lot of these things. Also, a lot of people take the square root of this. Yeah, so, and the ratio, and so forth. So these are all things that you have to live with. So you have to go through all these things if you want to be careful. But so this is kind of a weird thing. It's telling us that isostaticity doesn't really work for particles that aren't circular, but it's a really big part of circular particles. So what can we do to try to understand this? Okay, so we have made a hypostatic conjecture. We call these packings hypostatic because isostatic is exactly at the thing, hypostatic is lower, hyperstatic is above. So we're interested in these hypostatic things. And our conjecture is that you must have 2 things. And unfortunately, one of them is a knot of the other. So there's no way to not have knot in this thing. So, but you got to remember that. So if you want to be hypostatic, you have to have a rotational mode. So that's one of the criteria. You have to have a rotational mode. Discs don't have that, so they're isostatic. They're not hypostatic. Okay, they're going to be. The other thing you have to have, and every word here matters, we'll talk about each one, but the basic idea is that you're not a union of circles. Okay, if you're not a union of circles, then you can be hypostatic. If you are a union of circles, you will be hypostatic. Okay, so you'll be isostatic. Okay, so the circle breaks both of these and it's isostatic. So that's good. So we've got it so far. And this works for ellipses, which we've seen. Okay, so ellipses have a rotational mode. And you can't make an ellipse out of a finite number of circles. You need an infinite number to make it. Okay, and so that's hypostatic, and that's good. So those are two in our conjecture. But now let's focus in on another set of things, so we can sort of drill down on each of these points. So now we're going to build particles out of disks. So we'll build the particles out of disks, so we can build lots of interesting shapes out of these kinds of disks. And let's see what happens there. So our formula says that they have rotational modes, but they are made out of disks. So therefore, they ought to be isostatic. So let's see, are they isostatic? So when we jam these things, we have to talk about two different ways to count the number of contacts, because there can be multiple contacts per particle, because we have to deal with that. So for the bump particle, that is the real number of actual contacts that you have. That is always isostatic. Okay, that's always going to be 6. Every time, we never find anything. It's a running joke around the lab. Student comes in, I got 5. I got 5. I'm like, no, you didn't. You got 6. Figure it out. Come back. No, I got 7. No, you got 6. So eventually, it all goes to 6. We all get 6 when we do bump counting. But we can also imagine that we could count them in a different way. We could count the number of contacts between particles. In that case, each one of these only has 1. Okay, and in that case, just like for friction, it goes from 3 to 6. And in fact, this is a very good model for friction. We have a whole paper on how to make friction out of just bumpiness. And this is really what friction is. It's just little bumps on the surface. And the number of bumps sort of determines the number of contacts-ish that it can have. And so this way of counting gives us 2 ways to think about this. One which would be isostatic, and one which acts like friction. So let's see if it works. So here are the bump contacts, 6, 6, 6, 6, 6, 6. We always get 6. Okay, always 6. But if you look at the particle-particle contacts, then it depends on the acircularity. Okay, if there's circles, you get 4. But as you move up, depending on whether rotations win and you head towards 6, or friction wins and you head towards 3, you fill out this area between 6 and 3. Okay, just like it's friction. So we can also think of acircularity in another way. We can think of it like friction. Okay, so acircularity and friction both play very similar roles in what's going on. And so that's an important part of thinking about this. And here's, dimers going down, trimer, quadmer, blah, 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 12mer, whatever this is. And they look more and more frictional in that sense. We can actually quantitatively decide what the friction is. You can actually ask, for bumpy particles, what is the tangential force compared to the normal force? And it's just geometry, you can write it down. And so here are the mu values for a bunch of ellipses. And here, and in almost everything I've done, these are bi-disperse. So I don't have to worry about crystallization. When you have symmetries like crystallization, the counting can be a little bit weird because you can get hypostatic. So we just eliminate that by thinking about things that have 2 sizes. But here, we can actually do this analysis on different amounts of friction. That's sort of different amounts of bumpiness, how far apart the bumps are, how much they stick out, various things like that. And you can then get anything between 3 and 6. And here are real ellipses. These are bumpy ellipses. Here are real ellipses, the ones that are sort of the idealized version of this, when I go to an infinite number of circles. Okay, so bumpy particles live up to our criterion. So that's good. Let's see if we can sort of break this or try to understand. So how could we get something that was, check here, but not check here? We could, oh, sorry, I'll do that in a minute. Let's now go to circular lines. Okay, so we're going to go to circular lines. Okay, so we're going to go to these. We call these in general circular polygons, but if you just look at the one version, it's a circular line. Okay, so circular lines do both. Okay, they have both rotational modes, and they are not made from a set of circles. They have circles on the ends, but those lines can't be made out of a finite number of circles. So they should be hypostatic. We have to define their alpha. It's the same one, the array. This is also roughly the aspect ratio of this. If you work it out, it's a little bit not quite as close, but it's very similar to the aspect ratio as well. Here are the thing for it. So it starts out low around 4, and it goes up to 6, just like we expect. So these are hypostatic, but it's a little bit weird that it doesn't go down to 4. Okay, and that's a little bit weird. And so if we compare it to the ellipses, we see it's a little bit different. than the ellipses, and we'd like to understand how that difference comes about and what that is going on. And it comes about because with circular lines, you could have two contacts between the particles if they're face-to-face touching. So you could have a case where this is the closest thing and this is the closest thing. And that gives you kind of two contacts. But if they're short, if these things are short, that won't affect it very much. So there's a kind of variability in the how we should count this contact. And so if we count all of those contacts as one, we get down to 4 like we expect, and we get this curve. Okay. If we count them all as 2, then we get that curve that goes up. So it's a kind of interpolation between some of them are 1, some of them are 2. And so we would like to try to figure out which ones are which. How do we know whether it's a 1 or a 2? What contact? So we look to another way to think about degrees of freedom in the problem. Another way to think about degrees of freedom in the problem is if I bang it, what frequencies will it vibrate at? So I can ask, what are all the frequencies that this packing can vibrate at? So this is what we get by taking the eigenvalues of the dynamical matrix, the second derivatives of all the potential energies in the problem. And let's start over here. What I've done is I've written down the frequencies that I will get, log of frequencies, as a function of every eigenvalue, just ranked by their size. Okay, so I just start with the smallest one, I call that one 0, next one, keep on going. Let's start with something that's easy to understand. Let's start with the disks. So the disks only have 2n degrees of freedom. So it can only be 2n ways of vibrating. And those are all what we call translational degrees of freedom. They're all vibrating because that's all they can do. Rotating doesn't do anything. Okay, so that's clear. So everything on this side is translation. Okay, now if we go to a dimer like this, we have those translation modes, but we also have a bunch of rotational modes. And in the dimer, all the rotational modes are large sized. Okay, so this is large frequencies. These are small frequencies, okay, down here. There's also some 0 frequencies that we haven't shown. So there are a few 0 frequencies, because if the whole system were to move right, we wouldn't care, or up or down. And if the whole thing were to rotate, maybe or not, we would care depending on the system. So there are some true 0 modes that we haven't shown on here. But all the modes in the dimers count, and they are isostatic. So every mode is counted. Every mode is doing something in that case. Now, if we go to ellipses, we have this little region down here. And this little region down here is interesting because if we push a little bit, they'll go up. If we pull back a little bit, they'll go down. The whole idea behind finding these frequencies is that we think that the potential energy looks like a parabola. If the potential energy looks like a parabola, then I shouldn't care what the pressure is. I should get the same frequency regardless of what the pressure is. However, if instead of being a parabola, we're a 4th order function, then it's going to depend on exactly how much I push. What's the best parabolic approximation for each push? And so that's what's going on here, is that these guys are quartic modes. These are modes that are set up because we have a 4th order thing. I'll show that in a second. But let's look at the circular lines. We have the same thing, translational degrees of freedom, 1 in rotational degrees of freedom. And now there's a break. So there's this chunk down here, which move up and down with pressure, but there's this bit up here that don't. And as we move along here, each one of these represents a different alpha. So when we get down here, we're like a circle. And so if we're like a circle, all these are quartic or not good modes, and they're all down here. They've all fallen very far. But as we go more and more like this, we fill out more and more of those become, are able to get rid of degrees of freedom. So we now have a way to figure out which one is which. Okay, and this just works, as I said, because we are looking for the minimum of a packing. The minimum of a packing is usually a parabola. It's usually a parabola, but in these cases, it turns out to be a 4th order function. And that is the big difference with these. This is often called 1st order stable versus 2nd order stable. Okay, even though we're using square and 4th, it's because of the way you think about displacements as opposed to the potential. Okay, so circular lines are checks and checks, which means they're hypostatic. And now we also understand how to extract which modes are contributing to the hypostaticness of that mode. So now let's try to distinguish between these two by taking circular lines and not letting them rotate. Okay, so now what we're going to do is we're going to throw down a bunch of circular lines that have a fixed angle. That angle cannot change during the entire simulation. So grow them up, they can't change their angle. And so this would tell us these better be isostatic. So let's see what happens. So here, these guys can't rotate. So this guy had this angle when it started, it has this angle now. This guy had this angle when it started, it has this angle now. This is the exact same packing. We started with the exact same initial condition, but we let these guys rotate. So when these guys rotated, they made contacts and they are not isostatic. 5.6 is the isostatic number we need to get, and we got 5.8, or vice versa. We got 5.6 and we needed 5.8. This is supposed to be 3.8, it's supposed to be 3.8. That's what we get. Okay, so this tells us that rotations are really the critical thing that determines that. Okay, so let's now extend this to any shape. So essentially now we have any shape. Because if we can make any polygon, then we can make its circular version, and we can see, and of course, all we have to do on this diagram is just change circular lines to circulo-polygons, and then everything works out. And that's what we see. Okay, so circular lines, circular polygons, they all act the same. There's no difference. There's no difference between them. And so these kinds of shapes, or any shapes you can make out of this, will all be isostatic in this sense, or hypostatic in the sense that we can figure out where the extra contacts should have been. There are some details that you have to think about when you're doing this. Once you have something that's not just a line, there's not just one alpha. There's not just one way to define alpha. And so there's families. So like, for example, this guy and this guy are both isosceles triangles that are sort of the same longness. So they have the same circularity in some sense, but they aren't the exact same shape. So they have some difference. And the same thing goes all the way up to here. This is the most circular guy, the equilateral triangle. And what we find is, even though, and this is just triangles, it just has this one thing, but if we went to four-sided object, we would have a three-dimensional version of this, and there's so many degrees of freedom. But what we find, it's always the circularity. Okay, it doesn't matter whether there are other shape considerations. Like these guys, the main thing is the fact that they're elongated. And so that's the thing that matters most. And so, for example, isostatic is the possibility for these things, but they're often hypostatic. They're very often hypostatic. Yeah.
I'm
Sure.
sorry.
No,
to
please.
break the rhythm.
Please interrupt.
Sorry.
Yeah.
It's just that you did start, but I just need to clarify this thing about face-to-face contact. And you said it's subtle, but you have 2 points. You call it two contacts when it's face-to-face.
So we could call it either.
Yeah. Okay.
Here, we can go back to this.
What gets me, and maybe it's off the topic, is that in this situation you didn't say anything, but you use linear springs or something in those simulations.
We do use linear springs, but we've also done this with Hertz, and it doesn't matter.
So all this isostaticity anyway, it's about forces, but here it's really pressure distributions, and I'm like, I'm struggling with the idea here. Because
so what the difference is that if you change the potential, so if you have a Hertzian potential, the pressure dependence of these hypostatic modes will change. The fact that they're there will not change. The fact that they're there is geometric. The fact that they're there is the fact that there is an overlap.
Yeah.
Okay, so that doesn't matter. You don't care what potential you have there.
Okay.
What people do is they break up the potential energy into two parts: a geometric part and the forcing part, the work part of the potential. And the geometric part is just 1 or 0, whether I have a contact or not. And the forcing part tells me how it depends on whether I have a contact or not. And you break that up in that way, you have what's called a stiffness matrix and what's called a contact matrix. And the two together tell you the whole story, but it's the contact matrix that determines whether you're going to be isostatic or hypostatic. And there's an actual geometric interpretation, which I'll show in a minute. Does that make sense?
It makes sense.
Yeah, good. Yeah, please interrupt whenever you need to. Okay. So if we plot everything in terms of 1 minus alpha, this acircularity, then everybody sort of falls on the same curve. As long as we count the contacts in the way that we discussed by subtracting off any quartic modes. So as long as we subtract off any quartic modes, then everybody lies on the same thing, just based on circularity. Okay, it doesn't matter whatever anything else is going on. So these, decagons can be weirdly long shape with a little with an arm on it. They can be partially triangle, and whatever it is, doesn't matter. They all sort of follow the same. It's not exact. It's not a perfect universality.
I gotta interrupt you.
Yeah, please.
The first author was my student. I think also maybe someone else is here, student, Chris Santangelo's student.
Kyle?
Kyle, yeah.
Yeah. Oh, good.
Yeah, so
Great.
he's your first co-author.
Yes, he is. He's a great student.
Yeah.
We love Kyle, although we couldn't keep him in science.
So,
I'm
what
sorry,
I can't say anymore.
Right, yeah, exactly. Drag him back, that'd be great. Okay, so let's move on to the last one of these sort of things that I had talked about before, and that is the rouleau, the constant whittling. So these better be hypostatic, and if we look at them, they're hypostatic because they can be made out of circles. So this is a circle, this is a piece of a circle, but it's not a full circle. Okay, and so basically another way to make you think about it is, I can't make this point out of circles. I need an infinite number of circles to make this point. Okay, that's maybe another way to think about it, but that's why we add full here. Okay, so it must be it's union of finite number. We've already talked about finite number a lot of full disks. If they're not full disks, then you're going to have some kink somewhere, and that thing you either think about as not a full disk or it's something that's going to require many, many disks. So they're hypostatic because of that, and they count also. Now we can ask, what is this last word in here? Accessible. Okay, so now we have to think about it a little bit more carefully. What is accessible area? So it's the accessible area that matters. And so to sort of think about this, we've made this other shape, the dumbbell shape. Okay, so the dumbbell shape is a lot like the circular line, except the line part is thinner. So now we can make a distinction. On this side, when these two guys are touching, this is not a contact. Okay, so it cannot reach that portion that's not built by circles. So everything that it can reach is built by circles. So if everything that it can reach is built by circles, it's isostatic. And that's what we have here. However, in this case, now we make it long, now I can have a contact with that guy. Because I can have a contact with that guy, is now accessible. This region is now accessible, and so that has to be hypostatic. Okay, so that fills out our whole curve. So this hypostatic conjecture is proved, right? Mathematicians prove it. No, I'm just kidding. This is poor man's proof by computation, right? Very poor man's proof by computation. But we haven't found any counterexamples. I'd love to find counterexamples of this or other places where this doesn't work. Okay, so this is it's currently, we've never found anything that doesn't fit this bill. I could have told the entire same story by thinking about the density versus circularity. There's also a kind of master curve there as well. Okay, so there's a whole other story in the paper that Kyle helped us do, where we talk about this whole thing from the perspective of density. And there's a densest place, and it's always the same place. It always has to do with the circularity. It doesn't matter other things about the shape. It's sort of about the aspect.
What about like highly polydispersed?
So if you do, so this is always binary where the two things are close together, but 50% apart or less. If you go to highly polydispersed, you're going to start to get things that can live inside the interstices of the major packing, like the Apollonian packing that was talked about earlier. In that case, you're going to have something different. But the individual phases, if you break up one of those packings into big particles, as medium particles, small particles, and sort of gather them together, then within each one, they should obey this rule. Okay, also just note, you can do this, Kyle helped us with this as well. You can do this in 3D as well. Okay, so almost everything I said goes over to 3D as well. Similar way to think about that. Okay. Now I want to just talk about the geometric interpretation of this. So we have a way to figure out whether the contacts, how many contacts are hypostatic, or how many contacts we should count as hypostatic. But we don't know how to find an individual contact. Why is an individual contact hypostatic? Why does it become quartic mode instead of quadratic mode? So let's think about a circular triangle. So I'm going to put two small circles here, and these small circles are going to mean that this circular triangle cannot go up like this. So I've eliminated 2 degrees of freedom with this. I can't go up and I can't go side to side right here. So I've pinned this point. But we know in general to pin this whole thing, I need 4 points. I need 4 points to pin it. But I can actually pin it with 1 more point. So if I set this guy down here, if I set it in the right spot, then when it tips, it actually overlaps. But it doesn't overlap linearly, right? It overlaps by the cosine of this angle. And the expansion of cosine is displacement squared. And so I take displacement squared and put in the square of the potential, I get a 4th power. And so these kinds of contacts are 4th power contacts, okay? And that's the ones you have to look for. And when we go back and we look for these, it works on either side. So this thing cannot rotate anymore, but only 4th order, only to 4th order. And that's why it depends on pressure, because if I were to move this guy down a little tiny bit, that overlap would become smaller and smaller and smaller. You know, it's a very small contact, as opposed to these guys. These guys, when I move this guy around, I'm linearly changing the overlap. Okay, so that's the big difference between these. Okay, so just to wrap up this part, packings can be hypostatic if both of these things are true. Rotational modes and the non-accessible area is not the union of finite number of full disks. You need all those caveats to get everything right. Hypostatic packings are stabilized by these 4th order potential interactions, which are represented by quartic modes in the dynamical matrix. The number of quartic modes determines the degree of hypostaticity. You can just count the number of quartic modes to get that, or you can use this geometric origin to count the number of contacts. It should be either 2 counts or 1 counts, or they're counting double. There's several different options, but they all boil down to the same idea. The other really interesting thing, which I'm not going to talk about anymore, but is very useful, is that shape and friction play very similar roles in packings. The fact that you have anything that's not a circle is almost just like saying it's frictional. That's sort of the take-home message, that friction and non-circular are kind of the same thing. Okay, so that's that part. Any other, and we had a lot of questions, but any other questions about this part before I move on to the next? Just yes, please.
So I know you have lots of non-convex things here, so this is sort of a silly question. But the difference in this 4th order, if it's not only strictly convex, but it's positive curvature, then you get out of the sort of the.
Yes, so there's I should have said this in the beginning. We're thinking of things that we call convex, which means that locally they're convex. There could be global things, but locally, when you get down to it, the curvature difference is not big enough to make this happen. So we like to let the flat lines, but not anything more. If you go to truly convex things, you can get 1st order things that but what we usually think about there is if it's truly convex, you actually should treat that as 2 contacts. Because once it's truly bent over something that you pushed in, you're really touching it in 2 places or more, possibly, depending on what it is. So yeah.
So you had on the previous slide this comment about everything in 3D also.
Oh yeah, everything in 3D, yeah.
I mean, so I was sort of following along. Aren't there these hypostatic sphere clusters, clustered part spheres?
Yeah, so there are some more there are more caveats, and it's harder. It's also way harder to sort of we haven't exhaustively pulled this space, but the polygons is pretty good. But when you go to polyhedra, which would be the next obvious thing, it's just there's so many degrees of freedom. It's really hard. So there are a bunch of the 3D problem is not solved, but the outlines of how it should work are basically there. And the thing that definitely is there, we don't have the geometric interpretation. The thing that's definitely there is that quartic modes are the source of hypostatic regions.
And I guess it was sort of that plus the next picture with the.
Yes, exactly. Can we do this in 3D? No one has done this in 3D. There's another way to think about this where you can do it, which is to actually draw the constraint space. So I could draw in 4D. This has 4 things that I have to fit. I can draw that 4D constraint space. There'll be a 3D surface in that 4D constraint space, which represents these 3 guys. And if that curvature in that space is negative, then it counts as 2 contacts. And that also works in 3D, but there's no simple, easy way to see it in 3D, much harder in 2D. Yeah, absolutely. Yeah, good. Okay, so now we want to just make everything go off the rails, right? So now we're not going to let the shape be static. The shape is going to be responsive to the package. So we're going to add a huge number of degrees of freedom, all the degrees of freedom in the shape. Okay, so what we're thinking of here, deformable particles, we're thinking of cells like cancer, soft tissue, we're thinking about emulsions, this should apply to emulsions, bubbles, foams, plastic materials, clay, soils, any kind of soft, anything where I mush it and it does something interesting. You know, this is a soft material. Our model should model this. Okay, that's the idea. We want to be able to model anything that's mushy. Okay, and what we mean by deformable is specific. What we mean by deformable is that the shape is determined by the internal and external forces, and there are a lot of degrees of freedom to determine that. So you have to have degrees of freedom in the shape. They have to be part of the dynamical process, the degrees of freedom in the shape. But we want to have control over the shape. We want to be able to control it in a very specific way so that we can get any shapes we want. These are sort of generic shapes we're after. We want to be able to address every cell separately. We'll be able to do things to each cell separately. We want to be able to make the interactions between the cells arbitrary. Whatever interaction we think is useful, we should be able to do. We want to be able to do this in all densities. So we should be able to do this from dilute to packed to overlapped, whatever, everything. And it should be easily extendable to 3D. We want all these things. Okay, there is a model out there for deformable particles, especially for cells, which is really actually a very old model. I mean, it's really just a model for bubbles or foams. It's really a foam model, but it was applied to biology relatively recently. You know, well, I guess not that relatively anymore, but in the 2000s. The original model is from Laplace, so you know, whatever. But so the basic idea is that if we think of the vertices of some kind of deformable particle that fills the plane. So this is all these, each of these are cells. These vertices determine everything about the system in some sense. And so we can write down an energy function that depends only on these vertices that does some fun things. So if this were an actual foam, what we would be saying is that the area would be conserved. That would be one thing we'd be saying. And the other thing we'd be saying is that these lengths would like to go to 0. So if you say those two things, then you have a foam, a real foam. What the biologists did is to say, well, we're going to conserve the area. So we have a term in our potential energy that's the area of this guy minus some preferred area squared. So it costs energy to go off your area, it costs energy to go off. But we're also going to do that same thing with the perimeter. So now the perimeter is going to be conserved, unlike a bubble where it's trying to get to be as small as possible. It always costs energy to grow a bubble. So it's trying to get as small as possible. This wants to be a particular perimeter. And this is basically made for cells because cells, their border is created by a bunch of molecules. And when the molecules are all out there, you can't make it smaller than a certain amount. You can switch a little bit, but they bump into each other. You can't pull it apart very much, or the forces will mess it. So this makes them small. Okay. Again, you'll see this this term come up that we see all the time, which is the perimeter squared over the 4 pi times the area. We call this the shape parameter when we're here, as opposed to circularity or acircularity and the other thing, because, well, you know, because what we discussed before. Okay, so how does this actually work? It only works because area can be expressed in terms of the vertices. Okay, because area can be expressed explicitly in terms of vertices and perimeter can be expressed explicitly in terms of vertices, we can now take this potential, which is a function of the vertices, and we can differentiate it with respect to the vertex position. Those give us forces, and now we just have regular MD. If we just do regular MD on these vertices, and if we use this potential, then we get something that looks like cells. Okay, so that's the idea. And this is a very nice model, but it doesn't meet the requirements that we're interested in. So it is deformable. You can deform the particle. Particles do change shape when things happen. And you have control over area and perimeter, which is good. That's one of the things we want. But you can't set the individual motion of a cell. This guy, if I try to move this guy, I'm moving all these cells. I don't have individual control over each one. And also, I don't have a lot of extra degrees of freedom. If you actually count the number of degrees of freedom here, you just have 2 per cell. You have 2 extra degrees of freedom. So basically, all you're saying is they're the approximation of ellipse. Okay, that's all you can really say. That you're just saying the elliptical approximation for this is what you're getting. There's no way to adjust the particle interactions. So I can't change what happened. They're just there. You can't get to all densities. You can't get rid of, you have to have everything is filled with space. This is extendable to 3D, and obviously people know that's what Surface Evolver is. Surface Evolver is a very old program. It does this in 3D. In 2D, it's pretty easy. There's just the T1 transition. That's the only thing you have to worry about. But in 3D, there's I don't know how many. You guys must know exactly how many types of transitions are in 3D, but it's so much harder, much more complicated. Can be done, but hard to do. Okay, so what do we do instead? So what we do instead is we say, well, let's make every single particle its own vertex model. Okay, so now each particle is going to have a set of vertices that are given to it itself. Now we've added a lot of degrees of freedom. For every particle we add degrees of freedom. So we can add as many degrees of freedom as here as we want. So these particles have infinite number of degrees or arbitrarily large degrees of freedom. And all we have to do is write down a potential energy that only depends on the position of the vertices. And you might think this is kind of limiting, but it's not, because we can always take any function that depends on the volume and use the divergence theorem to find out what the dependence is on the perimeter. So we can take any function that we want on this volume and we can turn it into a perimeter function. Now it may be complicated, like this full elasticity with yielding and blah, blah, blah. It will be extremely super complicated. But for many of the things that we want to do, it's not so bad. But whatever we do, this function has to be a function of these vertices. So that's the key requirement. Yes.
Maybe you'll get here because you want individual, but you also want deformation. You get one-sided constraints, I guess. Yeah,
we're gonna be able to tell what the interactions is between the particles as well. Yeah, absolutely. And that's a good lead into this next line, which says once we have this shape function, which depends on the positions, we can get the forces from the shape, but we also can add interaction forces. We can also easily add driving forces that can be individual. We could add drag. You're pretty much the sky's the limit as to what we can add. Okay, so let me just go through a couple of these. We already talked about the spring force for the area. So we say that the areas want to be a certain value. You can actually derive this from the bulk modulus if you want. You'll get it slightly different, but this is a good approximation to it. What we usually do is not set the perimeter of the entire thing, but set the line length for each one of these. That's a way to set the perimeter. It's a little stronger, and it's mostly for computational sake because we don't like it when vertices pass each other. And if you just constrain the perimeter alone, the vertices don't have any reason not to just go past each other. That's just a problem. So we usually constrain each individual leg to be a certain value. But that gives us a constraint on the perimeter. That's all of these forces. Then for interaction forces, what we usually do is take the distance between a vertex and this line. Okay, and the line segment means it's also going to interact with these edges. This is a well-known thing. Basically, these are now, each one of these is its own circular line, as we discussed before. So that's the interaction that we normally take. And we typically just take a repulsive spring potential. So this is only true in contact when they're touching, unless they're attracted. We can also add attraction, in which case it'll be true for some small distance away. We can easily add driving to this. What we typically do, although you can really, it's just your imagination that limits you, is we do a kind of driving that can mimic two sorts of behavior in a continuous way. So one is like a Langevin equation. So I just basically move in a random direction, and I'm just adding temperature. So that's one way. The other way is I'm going to go for a little while in a direction, and then I'm going to change. I go a little while in a direction, and then I'm going to change. And that's taken up because what we do, we add a force in a random direction, but that random direction is evolved from an equation. So we have a kind of velocity for the how fast the angle can change. And so if it's changing fast, then it's just like random. It's no different from random. But it's changing slowly. It's more like run and tumble, which is what a lot of cells do. They go along and then I didn't find any food. Oh, okay, I didn't find any food. Okay, I go. So that kind of way of running can be taken up by this, just by changing the relative values of these constants. We can also easily add linear or quadratic, any kind of drag that we want to this problem. Okay, so obviously I made this list, so this list. But now let's see it in action. Okay, so let's first start to think about it with cells. Okay, so here is a packing of cells. So we grow these cells, we just randomly put them down, and then we grow them. You can see they don't have a defined shape until they start pushing against each other. But also you see it recapitulates the Voronoi, the vertex model, because here is now the vertex model. So it actually can do both. It can do the vertex model when it's compressed. It's got the vertex model in it, but it also can do lower density. Here, each particle is doing this run and tumble motion. So it's moving a little way and then it runs, it goes a different direction, moving a little way, runs a different direction. Same sort of idea, but each guy is controlled. It's very easy to mimic things like osmotic pressure. How do we do that? Well, we just say that the pressure depends on the concentration inside and outside, and that the area is going to be responsive to that. So here, I'm just raising and lowering the area of this polygon. So it expands and it gets large like a cell will. It'll build up and get puffy, like when you have a cut and you get inflammation, your cells all get puffy, or when you don't eat or drink all day, they get all crinkled up and go in. So this is just what's happening in regular cells. Now, these are some other examples of the way you might move cells around. These guys are growing on a plate. This guy is hunting food, so there's a background gradient where it looks, every vertex is kind of looking for food. Obviously, I work with Corey, so I have to pack these things, and this is a packing conference, so we've got to pack these things. So this is not cells anymore per se, but here we're just packing these things, okay? And so they actually do jam. You might think there's so many degrees of freedom, how could they possibly jam? What happens is, once you start pushing on the area, once you're pushing on the area, that's what jams it. So eventually you're pushing on the area and that jams it. And so you can look at the jamming of these things. So here, when alpha is small, they're just like disks. They're basically just like this. They want to be disks. If it was one, they'd be perfect disks. They want to be disks. They look like disks. They're mostly disks, and you get the packings like you expect for disks. But as we increase alpha, they start to bend in and become more polygonal, more polygonal. And then something interesting happens between here and here. There's still some free space here, still a little bit of free space here, but now there's no free space. So they fill all the space. So the packing fraction goes to 1. You can see it in more detail here. Here's a big open space, and that guy gets closed off by the time I get to 1.18. And it turns out the spot where that happens is 1.15. Okay, so at that spot, when you jam them, the only place you'll jam, the first place you'll jam is when they're all touching when you get confluence. And so that sets the sort of jamming point for these guys at that point.
So can you say why alpha should be 1, the jamming?
So you can get jamming for alpha 1. It looks like this. It looks like this packing.
Okay, so which one is this? Sorry.
Each one, yeah, exactly. Each one of these is a different jamming point. So each one has a different phi associated with jamming. When it's like a circle, it jams at 84, like circles do. When it's like a polygon, this is roughly what you get for a polygon. That's the alpha of a polygon. And that's when you fill all space when you work with a polygon.
Is it alpha of a hexagon?
It's not exactly, yeah, but I'll show you where it comes from. It's interesting. So where does it come from? Well, if you imagine just having disk packings, which is what we're sort of doing, I mean, to first order, we have disks that are growing. If you look at the Voronoi that are associated with each disk, and you ask, what is the perimeter and the area of the Voronoi? Well, the maximum value for the perimeter and area for Voronoi for random packing is 1.15. Okay, so that's where it comes from. It comes from the fact that we're growing into our Voronoi space. I'm a little cell and I'm growing, 5 minutes, thanks. So I'm a little cell and I'm growing, and I grow out until I fill my Voronoi space. What is that space? Well, that's just how equidistant from my neighbors. That's exactly what I have to fill, because Voronoi means till you're halfway to you. You just reach out until you touch your neighbors halfway away, and that's the space you fill out. So you keep filling that out, filling that out. But what happens when you go further? What happens when you go further? You have to go in. You have to go back in. You have to get some kind of evagination. And you can see that happening here. So by 1.12, we've got convex. We got concave things.
There must be some ensemble of polygons that need that.
Yeah. Yeah, I mean, it's the one that you get there. People know it. It's the distribution of the size of the polygons is also known for the point sphere process. I'm not going to talk about this, which is only 5 minutes, but everything I've done can be done in 3D as well. everywhere I say 3D, 2D, you put 3D. Everywhere I say area, you say volume. Everywhere I say polygon, you say polyhedra. Perimeters are surface areas. Edges are triangles. Vertices are vertices. There are edges also. You just have to look. Edges. I think we had another talk where we talked about how to intersect a polygon with a polyhedra with another polyhedra. Yeah, face, point line, line, whatever. There's 6 of them. Here's just an in action. This is just a deformable particle under gravity, so it sags. You know, if you can also push it between gravity. It also has this point where it's a little different point. It's a 3D version of that. Now it's interesting. Nature knew this, right? It's 1.15. We were all excited when we found this. You know, 1.15. That's great. You know, but nature knew this, right? This is a giraffe. This is cells. This is everything that you've ever seen that is sort of polygonal. This is the cheapest way to fill space. The cheapest way to fill space is to have your perimeter 1.15 of your area. Circles don't fill space as well, but nature's also smart. You could fill space better. You could have more perimeter if you wanted. If you needed more perimeter, like in your brain, you need more perimeter. Like in your gut, you need more perimeter. How do you do it? You just push out. These are all perfectly good jammed states. Look exactly like this. We have a nice theory for that. We might also be interested in how these things move around, what kinds of shapes we get when these things move around. So here are different values of alpha and things moving around. You stay sort of, let's say convex-ish here, but by the time you get to alpha 5, you cannot be convex. You cannot move around and be convex. You're just going to have these invaginations no matter what. Another thing we really like to do is to let nature decide what the alpha value should be. So how can we do that? We can make these guys a spring and a dash pot. So that what happens is if they're pushed on for a while, they'll change their shape. So they relax. They're going to relax to a value that we like. If you do that, now you get something interesting that happens. So here is fixed shape parameter of 1.15. Here is fixed shape parameter of 2. Here is free. And what you can see is they change their shape a lot. So they're almost perfect circles. And then they go to these really elongated things, a huge distribution. We were really excited when we saw these two things because if you ask for a shape 1.15, what you get is stretch. So we wanted 1.15, that's what we asked for, but the system, because of motion, pushed it to stretch it. But when we went on the other side, we asked for 2, it pushed it this way. So there's a special value where you don't get pushed. And so we thought, well, let's let nature decide. Well, nature said, no, you're not going to get that special value. You're going to get this weird distribution, which is in fact what you see in biology. So if you actually look at biology, you see is a peak at 1.15, this special value. And you see this huge broad distribution of things that really elongate when they need to move past something. I'm going to skip this because we don't have time, but we can add adhesion. I guess I should skip this too because I'm out of time, right? Yeah, but I'll just say one quick thing, since it's not actually 5, which is when it says I'm supposed to quit on the thing. Is that you can make this also. I hear people talking about minimal surfaces and things like that. You can also make this quantitative. So for a case like where this 3D version of a thing is well defined, we know that the real physics is that the area is proportional to the energy, and we add that. Then we can get things like a liquid bridge. This is the same exact model, and here's a fit, but there's no adjustable parameters. So here's the force that we calculate from the model. Here's the force that's calculated in the experiment. There's no adjustable parameters. You tell me the gamma, you tell me the volume. That's it. The thing does. So this is a very good way to solve problems with minimal surfaces, and especially where there's extra forces around. You can do a lot of cool things with these minimal surfaces. You can do a lot of things with that. I'll show you. This is elastic particles. They bounce around. These are plastic particles. So now they don't bounce back. So you make this bread piece by bumping into it. It looks like a shape of bread. So this is like clay or silly putty. These interact really well with other particles. So you can do anything where you want to have something soft with something hard. We're also interested in droplet breakup. So these guys are getting pushed through an array. This is like microfluidic array. We have some experimenters who help us with this. These are simulations, but the experiments do very similar things. We'll talk about that. You can add drag. Here's drag. These guys are coalescing to form a big particle. So you put these guys in a shear solution, it'll agglomerate and form these kinds of particles. We're very interested now in the dynamics, in the forces, the moduli and so forth. I don't have time, obviously, to tell you anything about that, but you can check out all the stuff we do on this and also stuff that I'm more famous for with granular fluids and temperatures there by clicking on this link. Thanks for your attention.
I think we might disagree on your definition of surface evolver, but one of the nice things about surface evolver is with, let me think in 2D.
Yeah, sure.
With perimeter plus an area constraint, you get the Lagrange multiplier is the pressure in the cells. Do you have the same thing with your other engine?
Yeah, you get the pressure right out. Yeah, the pressure is one of the things and actually most of the time we actually run these things at constant pressure. So you can set any thermodynamic constraint you want. So if you think it's TS that's important, you set TS. If you think it's VP that's important, you set VP. If you think it's both, what if you think it's mun? You can set any of those. We have access to all of them, and we can set them all in the potential and have that evolve with it.
So you can set the pressure in.
You can set the pressure. We can set the chemical potential. You can set anything that you want because it's all. We have access to every point in the system.
But is that over constrained to set pressure, volume, and
no? Obviously, we can't do both, but neither.
Okay.
No one, right? God can't, right? Nature can't do both. You can't set the pressure and the volume.
Okay.
See, one or the other.
Okay.
So the way I explained it was by the volume was controlling, but we often actually, in the real way we run it most of the time, we run it with pressure control as opposed in volumes, the responses.
Okay.
Yeah, subject. Before you put this slide up, I made some question about one-sided constraints. And then you showed that it was you're using a quadratic density. But the illustrations never showed any overlap. They would allow some overlap, but they never see that happening. So somehow it seems extra effective.
Well, we set K large.
That's enough. I mean, I can't see the resolution.
Yeah, so our goal for K is that the overlaps are always less than 1%. Because if you think about where you want the softness to be, okay, so you don't want it in the area because most of the time we're thinking about something that's incompressible like water.
Right.
And so you don't want the area shouldn't change. You don't want one cell to be inside another cell because that would cost a huge amount of energy. So you want that what can change is the length of the parameter. So that's the place where it changes most. That's why, so when we looked at how motion affects alpha, what's happening is to get a higher alpha, it's stretching the perimeter, not changing the area. Now you could make something like if it were bubbles, if it was a foam or something where the pressure inside was comparable to the other forces, or where there's pressure leak between the cells, then you would want to have that. You might be different which one is dominant, but we always try to make them hard when we're doing this. Okay, go ahead.
Yeah, I'm impressed by this new way of approaching problems which have been dealt with by the evolver before, because you clearly model bubble as individual things. A boundary between two is not just a line; it is two interfaces.
Yes.
Know whether they overlap or no. Isn't this a big problem of computational efficiency if you have a discretization with 1,000 facets per bubble to get it really right, and you have a large number of bubbles to check for each and every of the finite elements whether it's a little bit overlapping on the other side? You must have some computational trick which.
No, I run these on my laptop. That was the speed of these movies is about 3 times what it is when you just watch it on your laptop. The reason is because if you think about how surface evolver works or things like that, there's a few vertices that are key, right? And so there's a certain size of polygon that is important. So you don't really have to go very far above that. If you're thinking about it as a comparison to say something like surface evolver, in a 2D system, 16 is plenty. You never see a 16 gone in these things. So 16 is close enough to a circle that you can't tell the difference, and you never see a 16 gone inside one of these packets. So you don't need any more than that. Now, if you're worried about like, one of the things we've been interested in is you could also treat the area between them as a deformable particle. So imagine that this also forms a boundary. So here's a particle and here's another particle. This is also the boundary of another big, huge particle that fills the entire thing, right? You can also do physics on that. So like you can have a thick foam, or what we call them wet foam. You can have a wet foam where you're treating the fluid. You can have drainage in these things. And there you might worry about having enough points, because now maybe you have to worry about a little bulge here, things like that. But at any rate, it's way better than anything else you could imagine, because we're not treating anything inside. So we have a one-dimension loss. And at worst, we need 2 times the number of points in surface evolver, but we gain a lot of freedom by having it, because basically in surface evolver, all these points that are together would be 1 point. And so we just double the point. So it's really not that computationally intensive.
So we talked about, you two talked about jamming, and the terrible thing about jamming is that you've got a small length scale, which is the contacts, which goes to 0, and this length scale of the bubble size, which doesn't go to 0, and this brings you to crazy discretizations in the neighborhood of the contacts. This problem still remains, right?
Yeah, but it's problems that we've dealt with. We already know how to do that because we do it for disks all the time. So these are really just a bunch of disks. That's another way to think about it. It's the number of vertices times the disks per particle. So it's like 16 times slower than a typical thing would be. But we have GPUs and big computers now, so it's really not. But all those simulations you showed were run on my laptop while I watched the movie.
Excellent. And I think we made it is excellent that we still have more questions, which is a
I'll be here.
to the engagement. But I think we might, at work time, take the opportunity to thank Mark one more time.